Hello everybody, my name is Meng Wang. Now I'm recording homework 11 of probability and stochastic process. Now let's look at the first question. The stochastic process x of t is real WSS with autocorrelation Rx of tau and power spectral density Sx of omega. We need to show that Rx of tau is real and even, and Sx of omega is even and non-negative. Now let's look at the first question to prove Rx of tau is real and even. The question tells us x of t is real, so we could get x conjugate of t equals x of t. And Rx of tau conjugate equals expectation of x conjugate of t times x of t plus tau conjugate, which is equal to expectation of x conjugate of t plus tau times x of t. And this conjugate, we can move it to x of t, which is equal to Rx of tau. So Rx of tau is real because Rx of tau conjugate equals Rx of tau. And to prove Rx of tau is even, we need to prove Rx of minus tau equals Rx of tau. So let's look at Rx of minus tau. It's equal to expectation of x of t times x of t minus tau. So Rx of tau is even. The second question asks us to prove as x of omega is even and non-negative. S conjugate of omega is equal to the integral of R conjugate of tau e j omega tau d tau from minus infinity to infinity. We could rewrite it as R of minus tau times e j omega tau d tau, the integral of it. And we let lambda replace minus tau, and then we could get the integral like this. It's minus integral Rx of omega e minus j omega lambda d lambda from positive infinity to minus infinity. And this minus could change the spectrum to minus infinity to infinity. This equation is equal to S of omega, which means S conjugate of omega equals S of omega. So S of omega is real. And now let's look at S of minus omega. S of minus omega is equal to the integral of R tau times e j omega tau d tau from minus infinity to infinity, which is equal to, we could use lambda to replace minus tau, which could be written as R minus lambda times e minus j omega d lambda from minus infinity to infinity, which is the integral of R of lambda e minus j omega lambda d lambda. This is S of omega. So S of omega is even. Now suppose we have a LTI system like this with H of omega equals the square root of 2 pi times delta of omega minus omega 0. The expectation of absolute R of t square equal to 1 over 2 pi times the integral of absolute of h omega square as x of omega d and d omega from minus infinity to infinity. We replace this part with this equation, and we could get the equation like this. And delta omega minus omega has value 1 only when omega is equal to omega 0. So 2 pi over 2 pi is eliminated. What is left is x of omega 0. Obviously the expectation of absolute y of t squared is greater or equal to 0 for any omega 0. So for any omega 0, as x of omega 0 is greater or equal to 0. So as omega of 0 is non-negative. For the second question, it is suggested that the following functions of v has these three expressions. They may represent an autocorrelation function of a WSS stochastic process by setting v equals tau, or a spectral density function by setting v equals omega or both, which functions f of v may represent either or both. Explain your answers. Now let's look at the first question. Before we do this problem, let's look at some theorems. The first one, any non-negative function s of omega, there exists a WSS process x of t with s of omega. Second, any non-negative definite function r of t1, t2, there exists a process x of t with r of t1, t2 as its autocorrelation function. Okay, now let's look at the first function, f of v equals e minus absolute v. Suppose v equals omega, f of v is equal to s of omega equal to e minus omega absolute, which is greater than 0. The diagram can be drawn like this, which is greater than 0. It can be a spectral density of a WSS process. Second, if v equals tau, f of v equals r of tau equals e to the order of absolute tau. The Fourier transform of it is s of omega, which is equal to 2 over omega squared plus 1, is greater than 0, so it can be autocorrelation of a WSS process. So A could represent both. For the second function, f of v is equal to sine v squared over v squared. First, if v is equal to omega, s omega is equal to sine omega squared over omega squared, which is greater than 0. The diagram is like this. It's a sine wave. And if v is equal to tau, f of tau is equal to r of tau, which is sine tau squared over tau squared. The Fourier transform of it is 1 minus omega absolute over 2 pi if absolute omega is less or equal to 2 pi, and s of omega is equal to 0 if absolute omega is greater than 2 pi. The diagram is like this. So function B can represent an autocorrelation function and a spectral density of a WSS process. So it can represent both. For the third function, fv equal to 1 if absolute V is less than or equal to alpha, and f of V is equal to 0 if absolute V is greater than alpha. First, if V is equal to omega, f of V equal to S of omega equal to 1 if absolute omega is less or equal to alpha, and S of omega is equal to 0 if absolute omega is greater than alpha. The picture can be drawn like this. It's rectangular. So it can be because it's greater than 0, so it can be a spectral density of a WSS process. Second, if V is tau, f of V is R of tau. It has the function like this. We take the Fourier transform of it, and we can get S of omega is 2 alpha times sine omega alpha over omega alpha. The diagram is like this, which has some negative part. So S of omega is not non-negative. It cannot be an autocorrelation function of a WSS process, which means function C can only represent a spectral density of a WSS process rather than an autocorrelation. That's all. Thank you.